We are recording now, and this is a data science incubator again on data. And the first part is aimed to give an overview of what's the big picture and how to think about the way data flows in our work. And the second part is going to be specifically about one section of that workflow involving data. So the second section is going to be CJ. That's going to take up most of the meeting today. And the introduction should take about 5 minutes. So the this image, so to confirm, you see here something that on the top says the data science workflow. Yes, great, cool. So this image is kind of borrowed from the book R for Data Science and explains how a data scientist goes about doing their work. It usually involves, importing data from somewhere, then doing some kind of tidy stuff to take it to the shape that you need. And then you enter this loop where you usually transform your data to, for example, adapt better to a particular model that you want to run, maybe, or maybe you don't, but maybe you run a model, and maybe or maybe not, you do some visualization, and maybe you need to kind of enter this loop again until you're ready to communicate your results. So in this workflow, data is implicit. So at each step, connecting these multiple boxes, there is data flowing from one activity to the other. So I/O stands for input and output. So even if you are not saving data anywhere on your computer, you're still doing inputs and outputs because, for example, you may be reading data, that's an input, and then that data will be stored at least temporarily in your global environment, for example. So that is one operation where data is stored in the memory, and then you continue working. Say you tidy your data, and then you save, you assign the output to a new object, and that again gets kind of written in the global environment. In any case, what I want to convey now is that data is a central part of our work, and this figure here is my attempt to put data at the core of what we do, and a way to express more succinctly what the previous figure was trying to convey. At each step, you may be modifying the input data and producing some kind of new output. And where you store that depends on how complex is your workflow. Sometimes, again, you just cache that in your memory, in your R session, and it's gonna be gone when you restart your session. And sometimes you require to kind of save expensive computations in your computer or in a remote computer. So this data being here in the center tries to represent that you could be inputted from anywhere, even the original source, but then also you could be kind of writing data again to your computer or to GitHub or whatever. So data is certainly at the core of what we do. The best systems to manage data, and managing data has been the topic for the past 2-3 data science incubator meetups, and will continue to be for at least 2 more. So to manage data well, there are different systems, and the best of those will allow you to create like a local copy of that data and also a remote copy. So that data could be accessed from remote computers, from continuous integration services, and so on and so forth. So this is at the general level, and we are here not mentioning any tool in particular. Which tools have we been using? Well, for example, we have been using Dropbox as one of the tools that we use to store data locally. Dropbox already has a predefined location to store itself, kind of, it's usually it's kind of under the home directory, and has a name that starts something like Dropbox, and then parentheses and something like 2 degrees investing or something like that. And of course, it also provides this remote copy. So as you put stuff in your local folder, then Dropbox uploads it. So seen from that perspective, it is a relatively good system. But one problem that we have had is not in Dropbox itself. Dropbox has great uses. It is mostly in how we have been using it, because a lot of our code is written so that it calls, it reads data directly from our computers, as opposed to using, for example, APIs that query the data from the online Dropbox version, right? So here at the bottom, I have a link to the package R2drop package, which is a programmatic interface to the Dropbox API. And Pranav has used this before. You know, he presented this package to me, and there are, and he knows a lot. So you may, you know, book him in a help desk to learn how to use this API as a way to modify your existing code and make it, you know, right away a bit more portable. Because Dropbox reading from your local computer, what it does is ties all your workflow to your local computer. The color blue here is represented that anything around Dropbox is tied together and cannot be ported to, for example, a continuous integration service or to whatever else, because it depends on those paths written to your local computer. But if you just change that path and instead of calling a local file, you're calling a remote file, you should be good to go. Another alternative that is actually better suited is pins, and you know, I presented this package last time. Again, serve the same purpose. You know, you can declare with pins where that cache is going to be stored. You know, with Dropbox, it comes, you know, by default to, you know, home, Dropbox, and whatever else. With pins, there's also a cache. There is also a default, also under home, but you can change it, for example, to make it with to make the cache in your project itself, so that you can port your project along with the data that the project depends on. So you could use, for example, here to create a local cache in the project. And finally, it also has this remote option where you can set up a board, for example, a GitHub board, which is just, you know, an organization, an owner, and repo, and pins will do that for you. And you know, at the bottom again, you know, there is the link to pins package. So again, distilling what we were discussing, the essence of what we do is described by this figure. At the core, we have data, and today CJ is going to be talking about the very first stage of getting data from its first source, which is the database. So please, CJ, go ahead. I'm going to stop sharing my screen.
Unmute. Okay. Thanks, Mara, for that intro. And yeah, just to reiterate, we've been talking a lot about Dropbox and how we can move away from it or move to a better alternative. And I think what's become clear, at least to me recently, is that we need to look at the specific use cases and not like the full package all at once. So what I'm presenting today is specifically geared towards, if you want to get data out of data store, how can you do that? And I'm going to present an alternative way of rather than relying on these local paths to your Dropbox copy. So let me share my screen. Okay, and you can see my RStudio. All right, good. So I know some of you have probably used this before, but I have a suspicion that some of you have never used this before. But what I'm going to show you is how to connect directly to the database to get data out of the data store. And this is using primarily the package DBI. And so I wrote an example script here to run through some examples. Just going to load some libraries that I need later. And these are some functions that I wrote to manage the connection to the database. And I'll come back to these later, but I'm not going to go over them right now because I want to just show kind of the usage of it first. So what we normally do, or what we're often doing when we want to get this data from data store, is we are reading an RDS file or a CSV file. And in order to do that, first of all, we need to determine what the path to our Dropbox is on our local folder. Then we need to figure out this full subdirectory path to the file that we want. And then we need to read it in. And then, of course, it requires that this Dropbox, this 2DI Dropbox folder is on our local drive. So this is what we would normally do, set the Dropbox path and the project path, and then we would read in the file. And it takes a little bit. I'm using as an example this security financial data, specifically because it's one of the larger files that we use. It's about 200 megabytes. And then we have our data. And then we would move on with our analysis or code, whatever we're doing. Likewise, sometimes we're using CSV. It's very similar. story. We need to determine this Dropbox path, determine the sub path to the file, and then use read CSV to read it in. Takes a little bit of time. Get a bunch of warnings because I didn't specify the column types, which we've recently saw that can be problematic. But we have our data and we can move forward. This next few lines is how we might be able to do this if you wanted to connect directly to the database. So first, I have this function that I created, connect data store, that will connect us to the data store. And all the parameters are built into the function that I created. So we do that. We have our, oh, and now it's going to ask me for a password. So I type password. Okay. And now I use this command to access specifically this table within data store and save it as an object. And now I have the data from there as well. So as far as comparing these three possible ways of getting the data, the advantages of using, going straight to the database is, well, one, you don't have to depend on the name of the Dropbox folder. I've seen some cases where if someone has a business account plus a private account on their computer, then the Dropbox name might be different, or someone can actually change this to a custom name, and then it might be different. You don't have to figure out this proper file path that we're all used to finding in Dropbox. We don't have to worry anything about cross-platform file path formatting. So in this case, I use the FS package to figure out what this means going to the user's home directory, but the base functions don't do that properly across Windows and Linux and Unix types. So I have to do some special formatting there. We don't have to worry about that. You don't have to be connected to Dropbox at all. So you don't have to be connected to it. You don't have to be a user inside of 2DI, like you could be a separate user, and you don't have to have Dropbox on your local machine at all. And at least in the case of read CSV, you don't have to worry about the column types at all because it gets this metadata from the database and automatically does those column types automatically. And these explicit paths that we're so used to using, this makes it, as Mara said, very difficult in packaging this code for other uses, like using it on GitHub for continuous integration or building it into our packages. So the one disadvantage or possible disadvantage to this is that it does require you to have internet access when you make this connection. But there's are some potential workarounds for that by implementing these caching systems, whether it's the pins function that Mara talked about, or using the Memwise package to cache local copies of your data. And that could be able to work around some of the problems you might have from not having internet access. So because it does use internet access, some of you might be concerned about what the speed of this is. So I did some testing to see what this looks like. Let me clear this. So the first case, I'm going to read in the RDS file and then print it and see how long that takes. It's about 2.5 seconds. I'll do this with a CSV file. More than 5 seconds. I'm going to do this with my database connection, and it's 0.2 seconds. But that's a little bit of a cheat because, and it brings me to a point about what's happening here. So when you create this table, when you run this table function, what it creates is an object that's actually like a recipe for how to get this table. It doesn't actually get the data. So when I run this first command, no data has been downloaded yet. Once I print this, or I do something else to this that requires the actual data to be downloaded, then the infrastructure behind all of this will modify the query that it's sending to the database to minimize it to the absolute minimal amount of data it needs. And in this case, I printed the database, but it knows that it's only really going to show me the first 10 lines. And because of that, it only needs to know the first 10 lines. It doesn't know the rest of the data. So what happened when I printed this was it made the query, but it modified the query so that it only asked for the first 10 lines of this. And that's why it was so fast. So if I want to have a more fair comparison, this collect function, this will force this query to collect all of the data in this database, and then we'll have a better idea of how fast that can be. So I tried this out. See, it's taking a little bit longer, so that took me about 6 seconds. Now, to be fair, I also have a pretty fast internet connection at home, but I think it's pretty interesting that that time is comparable to, like, for instance, reading in a CSV file that's local on my hard drive. And then where this also comes into play, or in more detail, so as I said, this is just a recipe for the how to connect to this table. And if you do just typical dplyr commands to this, for instance, I'm just selecting here the first 4 or 5 columns and then collect it, you'll see we'll still get the same speed benefit, because again, once this collect happens, it's actually only going to request those columns and not the rest of them. So this should end up being a lot faster. Yeah, only 1.5 seconds. And that's kind of similar to what you're going to do in your analysis. You're going to read in this data, or for instance, you read in the RDS, you read in all those data, but then you do some things to it. You minimize it, you cut out columns, you keep the things you want, you join to another table, but you rarely actually need all of the data. So in that case, that's always the case, this database connection really shines, because you only ever import and request the data that you actually need. So again, one of the disadvantages of this is that it has to download over the internet, but as I've shown, if you specify only parts of the data you need, which is almost always, or it can still be pretty fast, and in some cases, it's even faster than reading the entire local file under certain conditions. So to give a practical example of this, I took this function from the PACTA analysis called get and clean fin data. And I made a new version of it called simulate, or it's called clean fin data. And it basically does all this stuff, reads in some other files, and it processes through this really large, nasty dplyr chain. But one critical difference I made is, rather than having the importing of the data inside of this function, I made the data a parameter to that function. That way I can read in RDS and then pass it to this clean fin data function, or read in from the database or CSV. And the point is here that I want to show what would happen if you read in the data given one of these ways, but then you did all that processing. That is very normal. And this is, again, this is at least based on exactly what we are doing in the PACTA analysis. So I load that custom function, and this is what happened when we do the RDS file. So it's reading in. That's going to take 2 to 3 seconds, as we've seen, but it's also going to process that file. So altogether, that took about 7 seconds. CSV, I'll do the same thing. Again, this took about 5 seconds to load the CSV file. Now it's going to process it. That took a little more than 6 seconds. Now I'm going to do the same thing with this database connection. And that only took 4 seconds. So in this case, at least, the using this database connection was even faster than using these local connections, because what was needed throughout this entire process of cleaning the financial data, it didn't really need all the data, so it didn't need to request all of it. So the download was actually rather small. Well, it was smaller than downloading the entire file. So again, this, but again, I've kind of cheated here because I didn't collect. So let's do this again, collect, and we'll get a realistic view of how long this takes. Yeah, 6.9 seconds. So it's a little bit slower, but it's pretty much on par with like loading in the full files from your local file. So I think that's pretty cool demonstration there. And I also have this little section about some sort of advanced usage of how you can use this. So say we were writing some code for the PACTA analysis, and we made our connection to the data store, and we made a connection to this security financial data table. And say we know later on that we know that at some point we're going to want to look up the big subgroup based on the ISINs in some of the data that we have, or the company name, or the coupon value. So what we could do is we could take this fin data object, which is the recipe to connect to this table in the database. We could add to it a selection that says, well, I'm only going to need these 2 columns, and we save that into big sub lookup, or the other 2. And now these things are new recipes, but the recipe now includes not only how to connect to the database and which table in the database to connect to, but it also contains this selection as part of its recipe. So if I look at this now, it just gives me those 2 columns, or company name or coupon value. And again, I can collect them to kind of see how long it takes to actually load these. And it's pretty fast because it's only those 2 columns that we're getting at a time. So now imagine we had like a data frame that had a bunch of ISINs, and I'm just gonna create one with some random ISINs pulled out of the fin data. So now I have this table that has some ISINs. If I wanted to join the big subgroup for these ISINs, I could do this: ISINs left join this big subgroup. This copy true is necessary, which I'm not going to explain because it would take too long. But and then I'm going to show all 20 lines, so we can do this, and it's pretty fast. You can load in the big subgroup, or if we wanted company name, or if we wanted to look up the coupon value, it's pretty fast. And of course, you could also do this directly from the fin data DB object that I made by just adding in a select directly to that, and it basically would achieve the same thing. And then just one point that I should make clear: when you do connect to these databases, you should always disconnect from it. My assumption is that the server eventually would drop your connection, but I don't know what the timeout is on that. So if we had a lot of people doing this all the time, it's probably ideal that you disconnect from it when you're using it. So that's the disconnect. And now I want to come back up here to briefly explain what's going on with this connection. So the primary thing that's going on is this DBI DB connect function. And you have to specify a driver. In this case, the server that we use is our Postgres server. So we use this package and function to set the driver. You need the database name, 2DII, the host, which is its URL, the username, and a password. This password, we don't want to leave this in code. So what I did here was I'm storing the password in an environment variable that is, it's maintained throughout the session. But if it's not there, I put this part in the beginning so that if it doesn't find that in your environment variables, then it runs this function, which will ask you for it. And that's what you saw in the beginning. This function asked me for the password, then set that as environment variable. Then it came back here and ran this with the password input. And you also need this options. Well, technically you don't necessarily need this options, but because of the way we're set up, the data is separated into these quarterly schemas, and this option setting will add a specific data quarter to your search path, and that enables you to access them much easier. So when you do this command here, rather than having to specify this schema, I can just put in security financial data, and it's going to automatically take it from the specified data quarter that I put in that search path. So that's it. We have about a few minutes to talk about this, so I want to leave some time for that. So I guess I'll leave my screen up, but we can go ahead and ask any questions if you want to.
Cool, thanks, DJ. That was really, yeah, that was a nice summary of the things. The one thing to note, of course, is, however, that a lot of our data doesn't come, so the other disadvantages, a lot of our data doesn't necessarily come directly from a data store. So while it might originally, there is then a sort of fairly computing intensive processing stage that happens before we've got the data ready for running through the portfolio analysis, which means that whatever we do, we will still need a local data storage location unless we shift this job to Taylor, which isn't really ideal for anyone yet. Watch out for the future.
Can we just host those handful of data sets, like the scenario stuff, on GitHub or also on a Azure type platform?
Yeah, I mean,
if you want to set it up, but I can't do that.
yeah. So
yeah, I'm done.
So that's why I clarified in the beginning, like, this is not resolving all problems, everything related to Dropbox. Certainly there's going to be other use cases where Dropbox is necessary, but this is one case, specifically getting this data from the database that data store is based on. This is one possibility. And then, as Jackson said, it could be possible if this was something that we wanted to use and it was useful and we thought it was like a better, or had advantages that we wanted to take advantage of, then possibly some of those things that are not currently in the database but are in the Dropbox, maybe they could be added to the existing database, or maybe especially with this potential divergence with asset resolution, maybe 2DI would have its own similar database that would contain all the files that we need. So those are possibilities, but yeah, it's true. This doesn't solve every problem for sure.
And the other challenge is potentially when you're rerunning a project from a later timestamp and you need to refer to the data store from a specific moment in time, even if it's 2019 Q4 data, if you need to go back and refer to the data, that didn't have that set of 10 companies or whatever it was in it, then that's also another challenge. But
so that's a great point, but I have a really easy solution to that. So for instance, if we wanted a connection to one of the previous versions, then at least the way the database is set up, we could do this. You can still see my code? So yeah, that's why I put in this data quarter thing, because you can specify which schema you're under. And the way it's set up, and maybe Taylor can speak more to this if he wants to, the data from this 2019 Q4 is in a specific schema labeled that, and the 2018 Q4 is
yeah. However, we get these data for 2019 Q4. I mean, I think we've had sort of, 4 or 5 drops of this in the past month, of which I've been working off a specific, truth for one project. Even if there is a later set of data referring to the exact same time period. But anyway, this is...
You mean if changes have been made to the data that's in the database that's in 2019?
Yeah, that's exactly what she means. Yeah, basically there'll be an update to like the emissions model or something that affects all quarters, or potentially just one quarter if there was a QA issue for one. And so that the update will just be added to the database, which then of course means that if you had that older data set, you lose access to it. I see a solution there of being potentially good about saving our project files or something of that, something in that direction, but I don't know enough about the workflow.
So I need to jump in to say that it's time to end, but I think that at least we are kind of exposing some of the perceptions that everyone has about how to go about solving this problem. I posted the link to the issue. It would be great if you can, log your ideas in that issue as comments, and then, we could kind of follow up on them. Maybe organize like a hackathon thing to just work, for 1 day or 2 days precisely on say, hey, I would solve the problem this way. Let's try to get it, done together and things like that. But that's a conversation to kind of follow up on. So sorry for that, and thank you for coming.
And also, just I will pass both of these R files over to Mauro, and you can add it to the repo. And if any of you want to try this at home, feel free. I'd actually be interested to see if anyone had any problems with it or successes with it. So yeah, test it out if you're interested.
We'll continue this conversation at least for one more meetup that maybe we will have the privilege of having Jackson presenting an entire cycle. Thank you.
Thanks, guys. Ciao.
Ciao, guys.
Thanks. Talk soon.
Thank you.